Hi there. Good afternoon, good morning, good evening, whatever time you're watching this. So this is Engineering with Trish once again. In our last video, I tried to answer your questions on the refrigeration cycle. But this time we'll go deeper and look at the differences between the idle cycle, the cycles you see in textbooks, and the actual cycles, like the name says actual, so the cycles in real life. So our presentation is titled A Comparative Analysis of the Ideal Vapor Compression, Actual Vapor Compression, and Vapor Absorption Refrigeration Systems. So what do we see here? I think now you all agree with me that heat flows was from a higher temperature region to a lower temperature region. That is what we see here. But refrigeration does the opposite. It moves heat from the cold region to the hot region. And that is why we need work inputs for this to happen. Okay, we also learned that every refrigeration cycle has four main processes: the compression process, the condensation process, the expansion process, and the evaporation process. Of course, the component determines the process. You should know that by now. And the difference between the systems lies in how compression is achieved. So you see here for the schematic drawing, I used a different symbol for the heat exchangers, that is the condenser and then the evaporators, but yes, so they are still what, rectangular in shape. So what is the idle cycle? I think I've mentioned this in class before. When we say idle, it's more like a perfect person. There is no one perfect, but the idle cycle is the perfect cycle. Everything is perfect. Compression is isentropic. We know what it means already, which means there are no losses, and the heat transfer is smooth, which means there are no pressure drops. So for the idle cycle, it's a perfect cycle. There are no losses, and then there are no pressure drops. So we see the components, or the components here nicely. And this diagram is a property diagram. So this here is the TS diagram, and we can see the idle process. For now, we don't have to know so much. We'll treat this as a topic later. We just have to know the property diagrams. How to draw will be treated later. So the straight lines indicate what? Perfect processes, which means no energy losses and no inefficiencies. Yes, that is why it's an idle cycle. So mechanical compression is what? 100% efficient. That is an idle cycle. Then we also learned that the performance of refrigeration system is measured using what? The COP, the coefficient of performance. And it is the ratio of the cooling effect to the work input. We can see that here, which means a higher COP means what? A more efficient system. But in reality, I think you agree with me, there's nothing like perfect. There's no Mr. Perfect, there is no Miss Perfect. Yes. When the refrigeration is working, or refrigerator is working, we encounter frictional losses, there are heat losses, and this all contributes to what? Inefficiencies. We also even have inefficiencies in the compressor. So all of this contributes to the inefficiencies in the actual cycle. So because of these losses, if you should draw the TS diagram of the actual cycle, this is how it will look, which means the cooling effect will reduce and this will increase the work required. So if now the cooling effect is less, that is the numerator is less, and then the denominator, that is the work impact required, is higher. What does it mean? It means that the COP will definitely not be as greater or be equal to the idle cycle. So usually for actual cycles, we have lower COPs. So here is the TS diagram as well. Now, what if we remove the compressor entirely? So that is the vapor absorption systems. The vapor compression systems require high-grade mechanical energy, that is electricity, to work. So it is very good. It is actually the most common. It's very good in places or instances where we have cheap grid power and then we have reliable grid power as well. But that's notwithstanding, we could entirely eliminate the mechanical compressors and replace them using low-grade, virtually free thermal energy sources, and that is the actual the absorption cycle. So we can see the two schematic diagrams. We see for the vapor compression refrigeration systems, you have the four main components. But for the vapor absorption refrigeration systems, the compressor is not there. It is rather replaced by a generator, a pump, and an absorber. So they achieve the exact same pressure transformation, but then the compressor is not part of the vapor absorption system. So here, the compression process is replaced by absorption, pumping, and regeneration. So pardon me, I have to put this in. Yes. So we see in the absorption, what we have low pressure refrigerants vapor, usually ammonia example. So here, usually we have two refrigerants. You have the secondary refrigerant and then the primary refrigerant. And then we see that it enters the absorber and dissolves into a transport medium, that is water. And then we have we have the lithium bromide and water, ammonia and water, so many types. I don't want to go there yet. Then we have the pumping. So a small low power liquid pump elevates the pressure of the strong solution. And then you have the generation, since the refrigerant is absorbed, there should be a generator that boils the solution. And then at the end of the boil, what happens? The refrigerant vaporizes at high pressure, and then the weak transport medium flows back to the absorber. We'll go here later. I don't want to burden you so much. You just have to know the differences. Yes. Now, absorption systems have lower COP compared to what the vapor compression system. Why? Because they use low quality heat and they are also cheaper. And then that's the downside to it. I think it's a question I'll ask later, so I don't want to give all the answers. So what are we saying? So we are saying that when you compare the vapor compression systems and the vapor absorption refrigeration systems, one, the compression systems was electrical or mechanical energy sources, but the absorption, they are cheap, like we said. So they can use waste heat, they can use solar heat, or even heat from steam. The compression mechanism too, this is mechanical compression, and then the vapor absorption system, so VAR, they use the absorber, the pump, and the generator. The working fluids too, yeah, so many of them there. Halocarbons and the fronts, I will discuss refrigerants later, so don't worry. This one, you have the ammonia water and then the lithium bromide water. Then the COP, like we can see, usually the VCC have higher COPs compared to the VARs. And then another thing is that the VARs, they were silent in operation because there's no compressor. Do you get it? Then the operating cost too can vary. Then the capital, of course, if you want it cheap, you have to put more money in, you have to invest. So the compression systems, vapor compression systems are lower, cost is lower, but then for the vapor absorption system, that should be tapping either waste heat, solar, or steam, they're actually very high. Capital cost is very high, but the running cost is lower. So someone will ask, Madam, then which of them is the best system? How do I choose the best system? Here, it depends on there are so many factors to consider, but I think the most important thing is that it depends on your energy source. If electricity is available, then why not vapor compression? And if you have waste heat available, lots of solar heat like we have here in Ghana, then absorption may be better. But like I said, you have to weigh your pros and cons. You have to weigh them. You have to weigh them because of the capital cost. Now, engineering is not only about choosing the most efficient system, but it's about choosing what's the most suitable system for the situation, which means that to know what to choose depends on you, the engineer. So that is it. Now, I have my first question for you is that, would you choose efficiency or energy availability? It's your turn. Please drop your answers in the comments. Then share one thing you have learned, ask a question, and respond to at least a colleague's contribution or submission. Who knows, your video will be featured in the next lesson. So till I come away again, it's engineering with Trish. Shalom for now.